All right, wave interference part 3. This is the case where we have two waves that are traveling opposite directions. And then we'll have an interference pattern. This is the one that we're going to do in our standing waves lab. I think I have that already posted and up, so after you look at this and work through homework problems, you can work through that lab. We set up waves on a string. But if you, again, do your trig identities for sine plus sine, then you end up with, you're going to add these two, in which case you'll get over 2. The 2 will cancel and you'll just get kx. You subtract them and you'll get omega t. That's no longer a standing wave because it's not kx minus omega t. So, I mean, it's not a traveling wave. It is a standing wave. So any one thing will be going cosine omega t, any one piece of the string, and then that will be spread out over a sine wave. So those are called standing waves. Every element undergoes simple harmonic motion. The amplitude depends on where you're at on the string. In standing waves, we have some places where we have maximum amplitude and places where we have minimum amplitude. Let's go look at a simulation here. Okay, so here's the string fixed at both ends, and we're going to vibrate it. See, that's not a wave that's traveling along the string. It's just a single, it looks like this is slowed up, but a single oscillation. So we've got a node, antinodes, and nodes. There's an antinode, and there's a node. Nodes where there's no vibration, antinodes where there's maximum vibration. And so any one piece is doing cosine omega t, but if you price out everybody's maximum position, then that's your sine wave. So it's broken it up into two pieces, the standing wave. So the nodes are going to occur when, again, we get n times pi. So when the x is a half number of wavelengths, and the antinodes, where we're going to have x will be a number of quarter wavelengths. Whenever sine can be plus and minus 1 is when we'll have an antinode. Whenever sine is going to be 0 is when we'll have a node. So sine 0, anytime you're pi, so we get half wavelength and quarter wavelengths. Quarter waves apart. All right, now go back to our simulation. So that's what we call the fundamental setup on that string, or you can vary the speed of the wave on the string, which changes the wavelength if the frequency stays the same. And there you've got two antinodes, or two segments. We'll call each one of these a segment. You notice each segment they're out of sync. We can do 3. We can do 4. So the length of the string has got two wavelengths on it. As you notice, if you were to freeze that, up, one down, you'd see that's one wavelength, that's two wavelengths. So the problems, now for a fixed end of a string, then that's where your nodes have to be. They're called your boundary conditions. Anyways, on a string, right? We did that. So there it is again. Usually, what we're going to do in our lab is our length of string will be fixed. We're going to remember that you still have the tension in the string. The velocity is dependent on the tension in the mu, and then you've got the velocity is lambda times frequency. So we'll adjust the speed by changing the tension in the string, which will change the wavelength since the frequency will stay the same. So the length, you just have to count number of segments and know the length of the string to know what your wavelength. This is one segment. Remember, we saw it oscillating up and down, so the length of the string is half a wavelength. And here we've got 2, so the length of the string is a wavelength. And here we got 3, so the length of the string is 1, 2, 3 half waves. And again, the frequency is going to be fixed on our experiment, and therefore we will adjust tension by hanging weights on the string. That'll change the velocity. Since the frequency is fixed, that's going to change the wavelength. Now, if we have, the string has to match the condition, so we'll find that there will only be one weight, one tension will give us this pattern, another tension will give us this pattern, and if we're in between, we won't get any pattern because the waves are not lining up. It's just give us any constructive or destructive interference, right? So we're getting constructive interference here and destructive interference here. Now for the string, there's multiple frequencies. If you can adjust the frequency and have the tension be the same, which is what happens on a musical instrument typically. If you have a string fixed at both ends and pluck it, then the simplest thing it can do is do its fundamental when there's only the one segment. That's the fundamental or the first harmonic. And then the next one would be when you can have two segments, and so the string with the same length and same tension can do either one of those depending on how you start it out. That's how you do a guitar, right? You hold down strings and cause a node to occur where you hold it down, essentially changing the length of the string and the notes. So, pianos and harps are different because you don't change the length of the string. You don't fret them, but you have different lengths with different densities of string. A given string can play these different frequencies, and we'll work that out as a problem when I post the problems. Now, the interesting thing about that is that's related. If you had a little chemistry, we've mentioned quantum mechanics. That's quantization when there's only certain patterns that you can set up. So in other words, there's only certain, you take that string and you can only have it vibrate in these particular ways. Any other way, you think with a wavelength, it won't fit on the string. It doesn't resonate with the string, and therefore you don't have a note. In terms of the atom, what people discovered in the early 1900s is electrons, as they orbit around the nucleus, don't really act like particles, they act like waves, and the reason they can only be in certain orbits is because that fits their wavelengths. All right, that ends this particular segment. We'll pick up, one more slide. Yeah, that's the way we're going to set up our experiment. We'll pick up with the next video here later.